In our next module, we're going to begin discussing how we bridge from ACI layer 2 to existing external networks. So as an agenda, we'll take a look at the overview of the need for L2 extension beyond the ACI fabric. We'll talk about different design options, and really this boils down to, do we want a contract or ACL to be used or not? And then we'll take a look at some design considerations, and a little bit later on we'll look at some common deployment and migration strategies. So let's take a look at an overview of the need for layer 2 extension beyond the ACI fabric. It probably goes without saying, but we're going to have ACI tenants, private network or VRFs, bridge domains, and even EPGs that in at least the interim, while we're doing migrations or integration of ACI to existing networks and migration of either traditional VLANs to creating ACI in a legacy mode, which we'll talk a little bit more later, which is a very common migration strategy or deployment method initially, or even whether we're doing it to the new ACI construct of creating these application profiles where EPGs truly define endpoints or types of endpoints in an application versus what I was just mentioning, the legacy model, where essentially our EPGs are a one-to-one mapping of EPG to VLAN. And really it's EPG to bridge domain to VLAN. So a VLAN ID comes in, it gets mapped to an EPG, and there's a one-to-one mapping. One bridge domain for every EPG, and one EPG and bridge domain for every VLAN. So that's the legacy way of migrating. It's the way that most people initially begin to migrate to ACI, and then they sort of do an internal ACI to ACI migration where they begin mapping out their true applications. No matter what you have, unless you're going to cut everything over on a single day, and I highly doubt that you are unless it's a very small data center or just a proof of concept lab, you will probably have the need for integrating layer 2 bridged connectivity. Now some people do choose to have no layer 2 connectivity to the outside data center and only have layer 3 connectivity. And in doing so, they essentially will move an entire VLAN from their legacy network over to the ACI fabric, and they'll already have their layer 3 OSPF or EIGRP or I or eBGP, whichever we want to use, which we'll talk about in the next module. They already have that set up, and so as soon as they turn on an SVI in the fabric and tag the subnet as public and go ahead and associate it to an L3 out, then this goes ahead and advertises that prefix to the outside world. They turn off their SVIs on the outside world, and essentially it's moving the entire VLAN over at once. You just have to be ready to move all hosts, bare metal or virtual, over at one time. And you don't have to move all of your hosts, just all hosts for one particular VLAN or subnet. So some people do choose to go that method, that route. But for most people, they do have external layer 2 connectivity. So there are some things to keep in mind. And here we just kind of see an example of extending L2 out for an internal VXLAN bridge domain to what's probably outside a layer 2 VLAN, which is also a bridge domain, of course. Remember, we've been calling things bridge domains for 20 years now, long before we just started calling them VLANs only. And bridge domain 1 is another VXLAN bridge domain that's exported or really bridged to the outside another VLAN. Okay? We also have some layer 3 extension, and we'll talk about those in the next module. So when we extend layer 2 out of ACI, we really have two ways to do this. We can either A, choose to use an EPG, which does not require a contract between the external VLAN and this EPG that we're using. It does, of course, still require a contract between this EPG and any other EPGs if we want to have communication there. Or we can optionally use a specific construct inside of ACI called an external bridge network. And this actually creates a new EPG for the external L2. And of course, a contract is required between this new external bridged EPG, or what we colloquially refer to as an L2 out, and the new or actually the new L2 out EPG and our internal EPGs. So the real question is, if we're creating a layer 2 out external bridge network, do we want to have it on the same layer 2 subnet or bridge domain, broadcast domain, as an internal EPG is using, but we want to have an ACL between it? Okay? And really that's all it would be used for. Actually, there would be one other option, and that would be flagging or marking, ingress marking or remarking layer 2 COS values. Okay, so layer 2 802.1p type of, or really class of service values. But there cannot be any, today, there cannot be any L4 through 7 service insertion between two EPGs that have the same bridge domain. So it would only be for an ACL or tagging QoS. So let's take a look at option 1, using an existing EPG. So here we have an example where we have, let's say, a virtual machine that we want to migrate over, or now has already been migrated over to the ACI fabric. It's on a leaf, and we've already created the EPG representation inside the fabric on the APIC, inside a given tenant, and we've tagged it to this particular port. If it's a virtual machine, we've probably done VMM domain mapping and probably pre-provision or possibly CDP LLDP discovery of the hypervisor host. But we also wish to have virtual machines that are outside the fabric be a part of the same EPG, not only for policy, but for any layer 2 communication between the virtual machines on the same subnet, as well as for any sort of firewalling or load balancing or anything else that's happening potentially outside the fabric and at some point inside the fabric. So what we'll do is we'll go ahead and, in this case, we have a back-to-back VPC, and we'll just go ahead and tag not necessarily these two ports, but really for each of these leaf switches, the VPC interface, and we'll tag it in this EPG. We'll tag it to VLAN 10. So .1q tagging, this essentially creates a trunk and allows that VLAN, but it also classifies as any traffic comes in from the external network to these leaf switches through or via these VPC interfaces tagged as VLAN 10, then it's going to be associated to this web EPG, and it essentially extends this EPG outside of the fabric. Now we do have to do a manual assign to the interface using something called static binding, which we'll take a look at the configuration for that in just a little bit. But they don't need to be connected to the ACI leaf port, no such thing. We'll talk about spanning tree and how that works in just a moment. So the workflow for this would be from the APIC. We would assign the port and encapsulation to an EPG. We would have to create and use a physical domain as well as a VLAN pool, and it would have to be a static VLAN pool. We're going to associate that EPG with the new physical domain, and we're going to map that physical domain to an AEP, to a particular interface policy group for a particular port on a particular switch. In this case, it would have been two VPC policy groups for leaf 101 and 102, probably a switch profile that encapsulates both. So here's an example of when we're creating an EPG, going ahead and mapping the path. In this case, it's node 17, switch 17, which really we can't even do anymore. This was an early screenshot. Port ETH15, and the encapsulation is VLAN 10. When we do so here's a screenshot of tenant 1, an application profile called app1, an EPG called web, and under web, static binding. Now, a little bit further south of here is the domain. That's where we would attach the physical domain. But here under static binding, we would have to do both. We would choose in this case, node 102, 103 VPC1. The VLAN 135 is in mode tagged. And we have a few different options here for the mode. The mode can either be tagged, which is an 802.1q trunk, and we're sending the VLAN ID. Untagged, which is essentially access mode, okay? Or 802.1p tag, which is kind of a misnomer because it tends to indicate layer 2 class of service, but in ACI, for some reason, it was named this, and what it really means is the 802.1q native VLAN. So there is one thing to note, well, a couple things to note. Really, in access mode, this port can only be in one EPG, and if the EPG already has a particular port in tagged mode, it cannot have another port or port channel in untagged mode, so access mode, which even if it's on if it's on the same switch, which kind of doesn't seem to make sense, because I could certainly have switch port mode trunk and then switch port mode access on two different ports in the same switch. But for whatever reason, what we would do here is we would say one port or port channel was tagged and the other port was 802.1p tag, or really the native VLAN. Okay, so it's still saying that the port is in switch port mode trunk, but then it's saying switch port trunk native VLAN, and then this VLAN. And that would be for another port on the same switch. And then under the EPG, under the Operational tab, and then under the Client Endpoints tab, we would see the learned MAC addresses. And for learning source, we would only see learned. Even if it's a VMM, we would never see VMM, just like if we were doing pre-provisioning. And also, one of the things that, I'm not sure if I have a slide for this in here or not, but under the bridge domain that this EPG is going to use, this bridge domain has to be set to, unless we're connected only to a particular host, but if we're connected to a switch, the bridge domain has to be set to flood for unknown unicast, as well as ARP flooding, okay? Because ARP flooding, or the removal of ARP flooding, no ARP flooding, and L2 unknown unicast through proxy mode, those are on by default in bridge domains, but those are really fabric innovations. And external switches don't understand that. So it's important that we actually have those modes set to flood, so that traditional switches will get ARP requests, as well as get L2 unknown unicast requests, where the end host might already know the MAC address for ARP, but we have, let's say, flushed a timer, a CAM table timer, or something like that. So option 2 is to use an external bridge network. So this is a specific entity or construct inside ACI that we'll take a look at under the tenant tab, called external bridge network. And we're extending the layer 2 VXLAN bridge domain outside of ACI, but we're not using an EPG to do it. And what this does is it creates a new EPG. So for instance, I might have an app EPG, a web EPG with VMs, and they could all be inside the same bridge domain, for instance. And of course, they have contracts between them to talk. But I now want to have another external, let's say, database, bare metal server, and it's either not been migrated or potentially never will be migrated over to ACI. And we still want that to be in the same layer 2 subnet, well, really layer 3 subnet, but layer 2 bridge domain. So in order to do this, we could simply have that port on that leaf switch tagged as a particular VLAN in one of either of these EPGs. We couldn't do it into both, but one of them. And that would put it in the same bridge domain. But then we wouldn't have any capability for ACLs or firewall rules between whatever's in whichever EPG we tagged it on and the external database server. So if we want to provide a contract or an ACL or any sort of QoS tagging, then what we'd have to do is we could actually create a new EPG, just a regular EPG, map it to a physical domain, which is the AEP mapped to this switch, node, and port, as well as a static VLAN pool, and go ahead and tag that VLAN in the new EPG, or we could create what's called an L2 external or external bridge network. And so by doing this, we then go ahead and extend the bridge domain outside of ACI, but we have to also have a contract. So the flow for doing this is we're going to create a bridged outside. We're going to assign the port and encapsulation to the bridged outside. It's going to force us to create an external EPG. We'll create the external bridge domain and the static VLAN pool, associate the EPG with the bridge domain, which is the external EPG, and then we're going to map the domain to the AEP, to the interface policy group for that port, and we'll create and assign consume provide contracts. So here's an example in the APIC of creating the bridged outside. We give it a name, we put it in an existing bridge domain and tell it what encapsulation, what node, and port, and then we create the external network. And again, here we can optionally tag QoS, but this defines the external EPG. And then after we do that, we see the new external bridged outside, and of course we have to create contract between, so here's just kind of for bearings, here's our tenant, our specific tenant 5.6. Under networking, so our EPGs are under application profile, but here we're under networking, external bridged. We create our L2 out and name it. Here we named it L2 underscore out. We give it a node profile or multiple node profiles, which is the switch and then the port. And then we create the network, which essentially creates the EPG. And to this network, if we were clicked on this here, we would see that we have to consume a contract. We could optionally provide one. Typically, we're going to be consuming one. And then we would have to provide the contract from the internal EPGs on the same bridge domain or different bridge domains, but really on the same bridge domain to allow communication. If it was a different bridge domain, it would be an L3 routed. So let's take a look at design considerations. There wasn't much to configuration, but we do have to keep in mind we could have layer 2 loops. So ACI does not run spanning tree at all. It's not running on the fabric, not even on the leaf switches on the access southbound. Of course, it's not running on the northbound because those are all L3 routed links using ISIS protocol to distribute all the routed and VTEP loopback information. But encapsulated in those L3 is, of course, our L2 VXLAN, and we certainly have the ability to form a loop unintentionally, and we have to be able to detect those loops. So we have a couple methods. The first is, let's say we had the same EPG attached to or mapped to each of these leaf 2 and leaf 5 ports, or sorry, leaf 2 and leaf 5 switch nodes, and then the ports on there. And what happens is that, let's say we have 1, 2, or 3, it doesn't really matter how many switches southbound, but we have a spanning tree root switch, and for whatever VLAN ID is traversing, BPDUs are flooded within an EPG, and so the external switches would capture this or catch this, and spanning tree would send one of these links into blocking mode. So essentially there is a built-in mechanism to allow for detection of layer 2 loops, and that is spanning tree. However, do note that between EPGs, let's say I had 2 separate EPGs, EPG1 and EPG2, they are in the same VXLAN bridge domain for whatever reason we chose, and actually we'll give a good example of that in a moment. It's multicast. But let's say 2 different EPGs, 2 different external VLANs, and maybe these are the same switches, okay? Maybe they're different switches, doesn't really matter. And so we have this layer 2 link, and we have spanning tree protocol that's blocking for, let's say, VLAN 10. Here, external to the fabric, so on this leaf switch facing this way, we have a block. As well as for VLAN 20, same thing on the external switches. But between EPGs, we have data that's going through. So spanning tree BPDUs are not flooded between EPGs. They're always flooded within, but there is a BPDU boundary, which is EPG. So in this case, we could potentially have a layer 2 loop if, let's say, for some reason someone configured access port, and it really wouldn't matter what access port VLAN 10, over here access port VLAN 20, and actually it would matter. So let's say we have 10 and 20, and so these are 2 different VLANs, right? But the traffic is being essentially bridged or merged inside the ACI fabric using the VXLAN, because the EPGs where we're ingressing VLAN 10 on this port and VLAN 20 on this port that are not blocking, they are a part of the same VXLAN. So the VLAN ID is dropped at the ingress leaf. We encapsulate VXLAN. VXLAN's carrying a spanning tree BPDU, but it's for VLAN 10. Now, if we ever look at spanning tree root priorities, we always set them on increments of 4096. Why is this? Well, because we have 12 bits for the VLAN ID, so the maximum value can be 4096. So the reason we set spanning tree root bridge priority on increments of 4096 is that the root bridge ID is always going to be or spanning tree priority ID, really, not the root bridge ID. The spanning tree priority is always going to be whatever value was configured. Let's say it was 4096. 4096 plus the VLAN number. So 4096 plus VLAN 10, we're going to have 5006, and plus 20, we're going to have 5016. So there are two different spanning tree priorities, two different spanning tree instances in the case of per VLAN or rapid per VLAN spanning tree. So because of that, data, even if the BPDU were flooded, it's not going to be the same BPDU. It's going to be locally significant to that VLAN ID. So having this would create a potential L2 loop. So how are we going to block against these sort of L2 loops? Well, this is where, and other reasons, other potential scenarios, is where we come into what's called the miscabling protocol. So the whole idea is that we're not going to run spanning tree inside the fabric ever, and essentially because that's what we're trying to get away from, right? Spanning tree is pretty processor intensive. It is, every time we receive a TCN, we have to drop or flush the CAM table. And of course, we do honor that outside the fabric. We honor both MST regions. We can configure the MST region inside the ACI fabric only to detect a particular multiple spanning tree or MST region outside the fabric. And based on spanning tree TCNs or topology change notifications, we can go ahead and flush the CAM table. And if we receive a regular spanning tree TCN, we can flush that CAM table. So that's fine. We still do that on the bridge domain where we have L2 extended. However, we don't want to be running spanning tree. So we need some very lightweight, low overhead, processor unintensive mechanism to detect layer 2 loops where miscabling or misconfiguration is done. So here we have the MCP. So the miscabling or misconfiguration protocol is going to help with loops. So here's a potential L2 loop, but where MCP is not needed. So here we have our two spines and our two leaf or top of rack switches. And we have two leafs connected together. Now we said originally that even in the case of VPC, we stray away from the old rule where two VPC peer switches have to be connected through a pair of 10 gig port channeled ports, right, or cables. And that forms the VPC peer link. So ACI does away with that, and you cannot, or you should not, and if you do, it will catch it. You should not ever connect a leaf to a leaf. You should only ever connect a leaf to a spine or to a host, or to an external switch or to an external router. Now, spines cannot be connected to spines ever, at least not today. Spines can, and they cannot also be connected to hosts. They can only be connected to leafs. And essentially, we're using LLDP, the link layer discovery protocol, with ACI specific type link values in them to detect if a spine's connected to a spine, if a leaf is connected to a leaf, or even to itself. And LLDP detects this, and so there's really no need for any sort of MCP. Okay? LLDP detects it. The fabric knows if it sees itself or another leaf switch or another spine, if it's a spine, to go ahead and disable that link. What if someone had configured, however, an LLDP disabled port policy or interface policy and group for these particular links? Well, in this case, we may need to have something, or these links here, we may need to have something that would detect that loop. So MCP would detect that and error disable one of the ports. In a scenario like this, where we have two top of rack switches, and one is connected to a switch, external switch, and another is connected to a router, right, for an L3 out, which we're getting ready to talk about. Well, this isn't a layer 2 loop, so MCP is obviously not needed. But what if this were another switch instead? Whoops. I think I accidentally pasted the same graphic twice. So pay no attention for the man behind the curtain. Just pretend this was a switch instead. I accidentally pasted the wrong graphic. And if this were a switch and not a router, then depending on our configuration, MCP might possibly be needed. So let's take a specific look at an example. We've got our two spines, our two leafs, leaf 101 and 103, each with port E133. And then we have a Nexus 5K. You could use multiple external switches. We're just going to use one, with ports E122 and 123. So here, looking at the configuration on the 5K, we see that we have VLAN 3444. We have another VLAN, but we're not going to use it. And on each Ethernet 121 and 123, we see that we're in switchport mode trunk, switchport trunk native VLAN 3444. So it's untagged, right? We're not actually sending the .1Q tag for this VLAN ID. And any traffic that we receive as a raw Ethernet header without a .1Q shim, we will insert into VLAN 344. So now we do a show spanning tree VLAN 344 or 3444, and we see that interface E121 and 123 are designated forwarding, and one is learning, but it should be forwarding soon. I happen to capture this. And the bridge is the root because it's really the only bridge. So now we go into the ACI fabric and access policies, and under global policies in the left nav, we click on MCP instance policy default. So this is a global policy that must be configured. And if you don't configure this, even if you have the interface policy configured, it won't take effect. You have to have the global policy configured. So we will provide a security key required, the administrative state of enabled, and loop protection action is port disabled. If we untick this box, then essentially we'll just go into a log every time we see a loop, but we won't actually disable the port. Now this loop detection multiplication factor, they could have just said how many packets do we need to see, how many looped MCP packets. So MCP is actually a layer 2 frame that gets sent out onto the wire. It's a very, very low overhead, and it requires very low CPU to process. So we essentially look for the L2 frame, the MCP frame that we sent out with our security key, so we know it's ours. And if we see it 3 times, then we're going to go ahead and we're going to send it every 2 seconds. So if we see it 3 times within essentially 6 seconds, then in this case we'll disable it. If we have this box unchecked, we'll just log it. Okay? And the initial delay. So the reason this initial delay is here is that we may want to prevent flapping. We also may not be going into forwarding mode right away. Spanning tree outside the network might go in, probably will go into, unless there is spanning tree port fast, or what is now called on NXOS spanning tree port type edge trunk, which I wouldn't recommend. At least not with your switches connected to a switch like the ACI fabric. But the spanning tree might go into blocking, listening, learning, forwarding. So we have that initial delay. You can customize that. Then under fabric access policies, under interface policies and the policies, we have our MCP interface. And this is actually enabled by default. And so really the default value is what is a part of the default fabric interface policy group, even if we don't configure it. But again, even if this is on, if the global policy is not enabled, then MCP is not enabled. So it's a good idea to configure this once and for all on all of your devices, and then not to disable it on your ports that are facing external switches. But it is probably something you do not need sent out to your hosts. So you don't want to overwhelm them or even just send them, unnecessary superfluous L2 tags. So now let's create a scenario that causes this L2 loop. So here in a tenant, in our overlay, we've got an application profile and two different EPGs, leaf 1, MCP leaf 1 and leaf 3 is just what we named the EPGs. They're both attached to a physical domain, which is where we have these node 101 and 103 ETH 133. Okay, so these are the breakouts of the EPGs under the static binding. And both, it's not pictured here, but both of these EPGs are a part of the same L2 VXLAN bridge domain inside the fabric. So notice the VLAN that we're encapping is VLAN 344 or 3444, right, for MCP leaf 1, but it's untagged. And down here, it's VLAN 3555, but it's untagged. And again, it really wouldn't even matter what VLAN we chose, as long as the AEP that we associated our physical domain with had that as a statically allocated VLAN block in the VLAN pool. Okay, so at this point, we're essentially untagged everywhere. Okay, so it's just raw Ethernet frames. And of course, remember, that includes our outside the fabric, our E122 and our E123. Those are both native VLAN. So spanning tree is up, it's forwarding on both ports, but we have native VLAN. And so regardless of the VLAN we choose in here, it's going to be untagged. They're a part of the same bridge domain. So at this point, we should begin to see on one of these switches, we are going to have the health score drop to 0. On the other, and it's only going to trigger on one of the leaf switches, so in this case only one of the EPGs. The other one would be at 100%. So if we take a look at the entire health score for the entire application profile, it's at 50% health, because one is at 0 and the other's at 100. And if we look, we can look under fabric policies. We could also look under our particular application profile, our tenant, our EPG, or we could even just look under system faults fabric wide. All of those places, we would be able to detect that a loop was detected on ETH 133. And if you double click on this, it would tell you what switch node. And so the port has gone down into port failure because of an MCP loop. So we do have a great safeguard against any misconfiguration or miscabling outside or even potentially inside or linked, leaf to leaf for the ACI fabric.